Welcome to our paper presentation about understanding privacy awareness in Android app descriptions. The title already suggests what this is about. We want to build a platform to identify critical discrepancies between developer-described app behavior and permission usage. Therefore, we leverage state-of-the-art techniques in natural language processing and deep learning. The outcome is a system that predicts the likelihood that an app requires certain permissions and that it can warn about descriptions in which the requested access to sensitive user data and system features is textually not represented. Platforms like Google Play distribute applications that serve a variety of different purposes. Among them, we also find mobile apps to manage passwords, track our health and fitness, organize bank transactions, or enable secure messaging. Users decide upon the trustworthiness of an application primarily based on the developer-provided description text and screenshots. The example on the right highlights the description text of the Google search app. As can be seen, the text is highly optimized towards explaining to the user the practical benefits of the app, promotes a rich feature set, but lacks information about how sensitive user data is processed. To protect security-critical device functionality, users are requested to explicitly grant or deny permissions that allow apps to access the camera, microphone, or other sensitive features. Since it was not always obvious which security implications it caused when users granted certain permissions, with Android 6, permissions have been reorganized into groups, whereas dangerous permissions subsume all those that carry a higher risk for abuse. As can be seen in the example with the Google app, the demand for permissions is quite exhaustive. If you recall the purpose of this specific app, which is to carry out an online search, and for example assist the user in finding nearby restaurants, it seems reasonable that the app also requires access to a user's location. While this permission request might still be very well comprehensible, others might not. For instance, it may be counterintuitive that the search app also wants to take photos or videos or to call phone numbers. In practice, the situation is aggravated by the fact that many malware and privacy-invasive applications also infamously claim more permissions than the functionality warrants. For instance, in a blog posting from September 2019, an antivirus vendor complained that even functionally simple apps that only allow to enable or disable a phone's flashlight request up to 77 permissions. From a functional point of view, there is neither a need for these permissions nor an explanation given by the developers that would justify the use of so many permissions. For that reason, making access to sensitive user data and device features transparent to users is of utmost importance in order to prevent unknowing or unconscious leaks of personal data. Descriptions of Android apps should imply the usage of dangerous permissions and highlight how and why they are required. The current status is that descriptions are mostly aimed at marketing features, but lack security-centric information. They are often minimal, inaccurate, or lack information about why certain permissions are required. Markets, besides performing security checks on apps, enforce no quality standards on how apps are actually presented there. The research questions we follow in our work are thus, how does an app description reflect privacy-related permission usage? And what is the relevance of individual words, word groups, and phrases within description text? The results of prior work in this direction confirms the existence of correlations between permission usage and individual word combinations. Sometimes, links between words and permissions are very obvious. For instance, if a text mentions location sharing, it can safely be assumed that this also implies accessing the fine-grained location. However, this doesn't work with low-quality descriptions, and in practice the vocabulary is often also not limited to just one permission. For example, let's take the phrase share photos and videos as shown in the screenshot. By seeing just these terms, they might refer to sharing pre-recorded photos, but they would not require access to the camera. However, since the subsequent sentence says, capture the moment with the messenger camera, it somewhat justifies that the app requires access to the device camera. This example shows that associating permissions with a certain vocabulary is inherently incomplete. Besides that, we found that existing studies operated mostly on less than 2,000 apps where description text were manually pre-labeled regarding the functionality an app provides. Since there is a constant evolution in functionality in description text, such approaches might not cover practical requirements. The key challenge, thus, is to find an approach that works reliably with noisy, real-world app descriptions and that can map privacy-related text to permission usage. To tackle the described challenges, we develop a system that can infer permission usage from the functionality described in arbitrary text fragments, even if they are of low quality. We therefore introduce a deep learning-based text classification approach that can identify sample-based correlations between part of the description and the permission groups and app requests. Our solution overcomes various limitations present in existing research and can work effectively with unlabeled, potentially flawed descriptions of real-world Android applications. We study the expressiveness of textual properties in app descriptions and employ an embedding model to capture semantic links between words, word groups, and phrases. Instead of linking individual permissions only with frequently occurring words, we perform a contextual text analysis using state-of-the-art techniques word2vec and GloVe, and, as introduced with Android 6, focus on groups of dangerous permissions. We train our network with 70,000 descriptions and sets of permission usage from real-world applications that are distributed via Google Play. We validate the performance of our model and evaluate the prediction quality for each groups of dangerous permission. To remediate the black box character that is typically associated with deep learning, we employ the model explaining algorithm LIME. Therefore, we calculate a score for each word that shows the significance for the output. Our approach comprises a training and a prediction phase. The figure on the right side highlights this process. The boxes in blue are the network input, the purple boxes are network processing, and the red boxes are the output. In the training phase, our network learns correlations between parts of description text and actual permissions of apps. In the prediction phase, our network receives app descriptions not seen during training. The output, as you can see in the boxes, is a list of permissions like camera contacts with a percentage scores that indicates the likelihood these permissions are needed based on the description. By applying the LIME algorithm, we avoid black box predictions and find what influences our networks to make these decisions. In practice, we find words and word groups that influence, for instance, the prediction of the context permissions. For training and prediction, we're relying on a convolutional neural network, or short, CNN. CNNs excel in tasks where positional features have to be extracted, which is also the case with text in natural language, and architectures for text classifications have been proposed on a character level or sentence level. In our work, we extend the sentence classification networks by Kim et al. That is shown in the figure. First, words are transformed to low-dimensional word embeddings and concatenated to form a matrix. Each row of the matrix then corresponds to one embedding. Word embeddings support the filter kernels of the CNN and learning generalizations of the input data. Each filter performs convolutional operations on the input matrix and stores the one-dimensional results in feature maps of variable length. Performing the convolution allows the model to disclose the impact of single words as well as of word formations. Here you see the CNN architecture that is based on a text CNN by Kim et al. Based on the data retrieved from the input layer, this means word embeddings of a description text, the network performs 1D convolutions with kernels of different size that are sliding windows that can process 1 to 3 words of an input. For each kernel, we allocate 1024 filters that learn the semantic context words appear in. After feature extraction, the 3 filter bands are reduced via global max pooling operations. As a result, we obtain the largest values of each kernel slice and concatenate them into a one-dimensional vector to fit the input of a dense layer. To prevent overfitting, we apply dropout regularization. The output layer represents the 9 permissions groups by single neurons, whereas each describes the usage probability with a score between 0 and 1. We evaluate our approach using real-world applications from the Play-drawn dataset. We opted for this repository of apps as it doesn't only feature raw app archives, but also provides metadata from Google Play, including the app description text, category, and download count. We downloaded 115,294 Android apps and corresponding metadata from this dataset. Then we filtered apps based on their text embeddability. After pre-processing each description, it had to consist of at least 20 embeddings from a pre-trained model to be used further on. This boundary was set to reduce the potential impact of insignificant samples on the training process. As highlighted in the shown table, we split the resulting set of apps into 3 subsets. The smallest one, the test set, includes 1,000 randomly chosen apps that are not used during training. The remaining apps are added to the training set, and 20% of them are randomly picked to be also part of the validation set. This partitioning scheme is required to prevent overfitting our machine learning model and to ensure meaningful predictions. We evaluated the performance of our CNN with the descriptions and sets of requested permissions for a total of 77,000 apps across training, validation, and test set. On this slide, you see the performance on a test set of 1,000 apps. The rightmost column shows the support, indicating the number of true positives found by a model. The varying number for the individual permission groups is mainly caused by their unequal usage in real-world applications. Overall permission groups, recall shows significantly lower values than precision. This comes from the fact that our dataset includes only unfiltered samples, of which many may have or have low-quality descriptions. As you can see, precision varies between 71% and 93%. External storage has the highest precision concurrently with the highest support. While camera, phone, and call log are on the lower end, calendar is worst due to its rare usage. To evaluate the impact of repetitively used words on predictions, we apply the model explanation algorithm LIME. Therefore, we extract all tokens from all app descriptions in our dataset, sort them by their frequency and LIME score, and repeat this process for each permission group. For demonstration purposes, we now have a closer look at the AndroMedia video editing app. On the left, you see the developer-provided description text. On the right, the permissioned usage as predicted by our system. By applying LIME, we obtain the words that are associated with each of these predicted permission groups. On this slide, you see the words that have influenced the prediction of the external storage permission. The tone of the color indicates its impact. For instance, the word export has a more significant influence than the term drop, for instance. Besides that, we also observe other effects of our learning approach in this slide. First, we see that the highlighted words are not very specific to storage. Of course, with a human understanding, we can somehow intuitively relate export or movie with storage. Still, for a machine learning system, this is interesting because the link is not obvious and outperforms a simple matching between words and permissions. What we also see is that word compositions are matched. In this example, we see that audio and files are matched. The different color tone means that each of these terms have different impact on a prediction. At the same time, it indicates that our network captures the co-occurrence of words. If we compare our predictions with the actually requested permissions, we observe some privacy-critical discrepancies. Or in other terms, the described app purpose does not correlate with actual permission usage. The AndroMedia app also requires granting the location, microphone, and phone permissions, but omits explaining their usage within the description. In fact, there is no obvious argument for a video editing app to need privacy-related permissions. In case they are required from a functional perspective, developers are encouraged to augment the text with an explanation on how they are used. To make this visually more appealing, we created a web application that enables a more detailed insight. Just to give an example, on this slide you see how it looks like for the Dropbox app. On the left we have the description text and all the words that influence permission predictions. On the right we have a comparison of predictions with the actual permission usage. By selecting the external storage permission, we see that the words that are linked to this prediction. Again, the color tone, which is blue here, indicates the relevance for the prediction. Selecting another permission, such as contacts here, again shows non-obvious links like videos or albums to somehow predict this permission. The reason our network believes that this permission is associated with these words emerges from countless correlations that were previously learned in the training phase. Apparently, these words and the context they appear in have been seen with other words, but in relation with contexts. So to sum up, our goal was to develop a system that can predict the likelihood that an Android app would require certain dangerous permissions based on the developer-provided description text. The use of a convolutional neural network enabled us to capture the context in which words occur and thereby outperforms purely NLP-based approaches. Our solution can be used to warn about privacy-insensitive description text and to raise awareness towards the explanation of security-critical functionality. We evaluated our system using more than 77,000 real-world apps and achieved a precision between 71 and 93% depending on the permission group. This inhomogeneous gap is due to the fact that we based our analysis on real-world dataset that contained many low-quality samples for training. To still better understand how predictions are made and to prevent the black box character that is often associated with deep neural networks, we applied a model explaining algorithm. If you're interested in the source code or want to see some sample reports our system produces, you will find them by typing the indicated links or by scanning the QR code. Thank you very much for your attention.